Good morning, everyone. I hope that your week's been going well so far and that everybody is still doing great. This is the final lesson in this modified version of Physics 30. This is lesson 30.25, which covers fission and fusion. And this lesson can be found on page 39 of your handout. What we're going to do today is go through what fission is, then we'll go through what fusion is, and end the lesson by going through some calculations that are used to determine the amounts of energy that fission and fusion can produce. And that energy can be used to run a nuclear reactor. So what nuclear fission is a process where you take a large nucleus. Enrico Fermi did this almost 100 years ago with uranium-235 nuclei. And uranium-235 is a pretty stable nucleus, but when the nucleus of uranium-235 is hit with a neutron, as long as the neutron is not moving too fast, the neutron will embed itself within the uranium-235 nucleus, creating a new intermediate nucleus that's very unstable, but it now has an extra neutron. So when that neutron is added to the uranium-235, you get uranium-236, but uranium-236 is incredibly unstable. And as a result, it breaks apart. And under the right conditions, it will break apart to produce barium-141, krypton-92, and then we also get 3 other neutrons. Now let's talk about the neutrons on both sides of this equation. The neutron that hits the uranium-235 is called a slow neutron because if it's moving too fast, it will do one of 2 things. It will either pass right through the uranium-235 nucleus, so it will not produce uranium-236, or it will just ping off of the uranium-235 nucleus. It's got to be fast enough to embed itself within the nucleus, but slow enough so that it doesn't pass right through the nucleus. It turns out that the 3 neutrons that are produced in this fission change happen to have that same speed. So what nuclear fission is, in general, is when you take a nucleus and cause it to break apart into smaller nuclei. Now you'll notice that energy is produced in this change, which means the change is exothermic, and what that means is that there must be a loss of mass. So any nuclear change where you get a large nucleus and you somehow cause it or entice it to split into smaller fragments is called fission. During the reaction, there will always be a small loss in mass because fission is always exothermic. And it's that loss of mass that accounts for the production of the energy. That loss in mass is converted to energy, and that energy is expelled to the environment. What this looks like graphically is we have to the left of this diagram the uranium-235 nucleus and a neutron, and then to the right we have the barium-141, we have the krypton-92, and we have the 3 neutrons. And it doesn't matter what you put on the vertical axis. You can put energy on the vertical axis because since this change is exothermic, there is less energy in the system afterwards. The energy that's missing is expelled to the environment, and that's what exothermic means. Or you could label that vertical axis as mass because the mass decreases as well. But the bottom line is fission involves taking a large nucleus and splitting it into smaller nuclei. Of course, if you know the change in mass, then you can use Einstein's mass-energy equivalence formula to find the energy released. In the above example, those 3 neutrons are also moving, as I said earlier, at just the right speed. So if they collide with 3 more uranium-235 nuclei, each of those 3 will undergo fission, producing 9 neutrons, and those 9 neutrons are going to interact with 9 uranium-235 to produce 27 neutrons when those 9 uranium-235 undergo fission. Those 27 are going to react with 27 uranium-235 to produce 81 neutrons, and this is what we refer to as a chain reaction. It's an exponential change, or in some math courses you might call it a geometric progression. Regardless of the use, whether you use the energy for good by powering a nuclear power plant or for evil by creating a nuclear bomb, the products of this fission reaction are highly radioactive. And in fact, this is an interesting thing, every single fission reaction that we have ever, as a human race, investigated always produces radioactive products. Which means that since the products are radioactive, they're hazardous to human beings and to the environment. Now, I should point out to you that this example of nuclear fission that we've been using to understand fission is just one example. Under different conditions, you can get uranium-235 to undergo fission and produce different isotopes. You might get barium-140 and krypton-93. Or you might get entirely different elements. So don't think that this is the only fission reaction that we ever learn about, because a fission reaction in general can produce any number of different isotopes. And it doesn't have to be uranium-235. It could be plutonium that undergoes fission. So now let's talk about nuclear fusion. In general, fusion is the opposite of fission, but not opposite in every way. So where fission takes a large nucleus and causes it to break apart, fusion takes smaller nuclei and causes them to bond together to form a larger nucleus. Same as fission, fusion reactions are also exothermic. So when I said that in a general way fusion is opposite to fission, it's not opposite in terms of the changes of mass and energy. Fission has a loss in mass and a release of energy and is exothermic. Fusion has a loss in mass and a release of energy and is exothermic. They are both exothermic. A very good example of this is one of the fusion reactions that occurs on our sun and on most stars, which is the fusion of hydrogen. There are other fusion reactions going on the sun as well, but this is the fusion reaction that starts the whole process. Under very high temperature, you can get two different isotopes of hydrogen, specifically hydrogen-3 and hydrogen-2. Hydrogen-3 is sometimes called tritium, and hydrogen-2 is sometimes referred to as deuterium. So if you happen to run across those words, they're just another way of saying hydrogen-3 and hydrogen-2. And under the right conditions, if they are moving fast enough, these two nuclei on the left of this will bond together to produce the helium plus a neutron plus energy. So again, whether we are talking about looking at this graph as being representative of mass or representative of energy doesn't matter. The mass of the hydrogen-3 and the hydrogen-2 added together numerically is going to be more than what you get when you add the mass of the helium-4 and the neutron together afterwards. So as well as having a loss of mass, you have a release of energy, which is why, again, the energy is written on the right-hand side of this equation. And again, if you can determine the loss in mass, then you can use Einstein's delta E equals delta mc squared formula to determine the release in energy. One really good advantage of producing energy from a fusion reaction is that the products are non-radioactive. When you look at the products of this fusion reaction that we've been talking about, one of them is a neutron. Now, neutron radiation can be hazardous, but it's very easy to set up a shield to absorb the energy that those neutrons have. The only other product of this fusion reaction is helium. Helium, as well as being non-radioactive, also happens to be what we call an inert gas or a noble gas. It isn't even chemically reactive, so it's perfectly safe. In terms of usable energy, this is the type of nuclear reaction that we would like to use in power plants because it's clean. It is perfectly clean. There is nothing at all harmful produced in nuclear fusion. In fact, as I've already said, this is where we get all of our solar energy from. Really, what the sun is a nuclear fusion power plant that's natural. It's not yet attainable, though. Nuclear fusion in a power plant on Earth has always seemed to be 30 years in the future. When I was in high school in the mid-80s, I always remember my chemistry teacher and my physics teacher being very excited and telling us that in 30 years from then, we would have as much energy as we wanted to, because by then they will have solved the problem of how to create stable, operating nuclear fusion power plants. And if you were to look online today, 30 years from now is kind of when we are hoping to have working fusion power plants. It always seems to be about 20 to 30 years in the future. In a little while, I'm going to explain to you why nuclear fusion is such a huge, huge problem to solve in terms of building the technology on Earth. Remember that both fission and fusion are exothermic. Going through the differences and similarities between them, just in general, fission involves taking a large nucleus and splitting it into smaller pieces. Fusion involves taking smaller nuclei and bringing them together to produce a larger nucleus. With fission, you produce radioactive waste. With fusion, the waste is non-radioactive, so it's perfectly safe. One of the things we haven't talked about is the fuel required for these processes. The fuel required for fission, let's just focus on uranium-235, is limited. There's only so much uranium-235 we can mine out of the Earth. And it's also very expensive to refine, to purify, because when you get uranium ore out of the Earth, it's only about, I believe, 1% of it is uranium-235. So the uranium-235 that we need for a fission reactor to produce electricity to run our lives, that uranium-235 is mixed in with a whole bunch of other isotopes of uranium. It's very, very expensive to extract that uranium-235 and purify it. For fusion, all you need is hydrogen-2 and hydrogen-3, and you can extract hydrogen-2 and hydrogen-3 from seawater. And it's very cheap to do, and there is tons of water, lots of water out there. So the fuel for fusion is very plentiful, and it's very cheap to produce. As I've said, we already use the process of nuclear fission in electrical power plants. We do not use fusion for power plants because it's still experimental. Now, why is it experimental? In order for you to get hydrogen-3 and hydrogen-2 to fuse together, you have to have those nuclei moving very, very fast. Now, why do they have to move very fast? Because they're both positive particles, so they will repel each other. And they will continue to repel each other until they get within a femtometer. A couple of weeks ago, we talked about the different forces in nature. And the force that holds a nucleus together, the force that attracts protons and neutrons to each other, is called the strong nuclear force. The strong nuclear force doesn't exist unless you can get those particles closer than a femtometer. And the only way you can get a hydrogen-3, which is positive, and a hydrogen-2, which is positive, closer than a femtometer, is to have an incredibly high temperature, talking about 10 million degrees for a temperature. And by the way, at that temperature, it doesn't matter whether I'm talking about Celsius or Fahrenheit or Kelvin. It's a big temperature. So the problem we have with building nuclear fusion plants is that we have to have something that can contain all of the nuclear fuel at a very, very high temperature. That temperature is needed to get those particles moving fast enough so that they can overcome the repulsive electric force and get within a femtometer. So there are reasons why fusion is not really being used in power plants. We have a lot of research yet to do in that area. Both of these processes are exothermic, and both of them have a loss of mass and a release of energy during the process. So we're going to do some examples now. The examples are just going to be applications of E equals mc squared. If we go back to our illustration of fission, where we have uranium-235 plus a neutron producing the barium, krypton, and 3 neutrons, we can use the mass of all of those pieces to determine the energy released. What we are going to have to do is calculate how much mass we have before the nuclear change and calculate how much mass we have after the nuclear change so that we can compare the two. I'm not going to be writing down all of these numbers. To find the mass of the materials that we start off with, I simply have to take the mass of uranium-235, which is 3.9029, multiplied by 10 to the negative 25 kilograms, and add the mass of a neutron, 1.6749, multiplied by 10 to the negative 27 kilograms. So this is the mass of what I can refer to as the reactants. If I want to find the mass of the material that we have afterwards, which I suppose I can call the mass of the products, I have to take the mass of barium, which is 2.3898 multiplied by 10 to the negative 25, and I have to add the mass of the krypton, which is 1.4765 multiplied by 10 to the negative 25 kilograms. And I have to also add 3 multiplied by the mass of a neutron, what this gives me afterwards is 3.916547 times 10 to the negative 25 kilograms. So we have a very small loss in mass, but there is a loss in mass. Let me write down what we have before. We have 3.919649 multiplied by 10 to the negative 25 kilograms. And then afterwards we have 3.916547 multiplied by 10 to the negative 25 kilograms. There's a loss in mass. This loss in mass is going to relate to the change in energy. If I calculate the loss in mass, delta M, I can take the final mass minus the initial mass. Again, I'm not going to write down all of these numbers. The final mass is the current number on my calculator, and now I'm going to subtract the initial mass, which is 3.919649 multiplied by 10 to the negative 25 kilograms, which gives me a change in mass of negative 3.102 multiplied by 10 to the negative 28. Kilograms. If I want to determine the release of energy, then I can go one step further. The change in energy is equal to the change in the mass times the speed of light squared, which means all I have to do now is multiply that change in mass by the speed of light squared. And this gives me negative 2.79 times 10 to the negative 11 joules. That negative is simply telling us that since the change in energy in the system is negative, energy was released. So the amount of energy released is that many joules. 2.79 multiplied by 10 to the negative 11 joules released. We certainly could determine how many electron volts that is. By now, converting joules to electron volts should be really a trivial case. you simply divide by the number of joules per electron volt. So we get, in terms of millions of electron volts, you get 174.5 millions of electron volts. Of energy per nucleus. This is just for one nucleus of uranium-235. If you had like a kilogram of uranium-235, which would have, we could work it out using the mole and chemistry, but which would have, I'm guessing, in the order of 10 to the 24, roughly, to 10 to the 25 nuclei, you would have 10 to the 24 to 10 to the 25 times more energy than this number. All right, and B, we're going to do the same thing, except we're going to be doing it for the fusion reaction. I'm not going to write anything down for this. I'm going to show all of my work on my calculator. If I find the total mass before, I can take the mass of the hydrogen 3 and add the mass of the hydrogen 2. Which gives me this much mass in kilograms before. When I look at the mass afterwards, that would be the mass of the helium-4, which is 6.6463 multiplied by 10 to the negative 27, plus the mass of a neutron, which gives me this number. If I take the mass that I have afterwards, which is the number that we're looking at right now, and subtract the mass that I had before, which is 8.3526 multiplied by 10 to the negative 27, I get a change in mass of negative 3.14 times 10 to the negative 29 kilograms. If I multiply that by the speed of light squared, I'm going to get the energy released in joules. And then if I divide that by 1.6 multiplied by 10 to the negative 19, I get the release of energy in electron volts. If I divide that now by 1,000,000, I get the number of millions of electron volts. So this is the change in mass. This is the energy released in joules. This is the energy released in electron volts. And this is millions of electron volts. Now C asks us to do a number of things. The first thing is to go back to our fission reaction, which I have at the top of the screen here, and calculate how many joules per kilogram of reactant. On the right-hand side, I have the energy in joules. It was 2.7918 times 10 to the negative 11 joules. If I want to find out the energy per kilogram in units of joules per kilogram, then I need to take that energy of 2.7918, I'm not going to use the negative, times 10 to the negative 11, and I need to divide by the kilograms. Now it says in the question per kilogram of reactant. So the reactant is the stuff that's on the left-hand side. I need to divide that energy by the number of kilograms we started off with. So I'm going to divide by, in brackets, the mass of the uranium, which is 3.9029 multiplied by 10 to the negative 25, plus the mass of a neutron, and I see I forgot my decimal up there. This should be 2.7918 times 10 to the negative 11. I'm dividing by the mass of the uranium plus the mass of the neutron. What that gives me is approximately 7 times 10 to the 13 joules per kilogram. I'm not going to worry about the decimals because that is not the point of what it is we're doing here. We get approximately 7 multiplied by 10 to the 13 joules per kilogram. Another useful measurement of how powerful a nuclear change is to take the electron volts and divide by the number of nucleons. So the second part of this is saying how many electron volts per nucleon are produced. Well, I'm going to take the number of electron volts, which was 174487500, and I'm going to divide that by the number of nucleons. So I divide by 236, and I get this number, and I'm just going to round that to 7 times 10 to the 5 eV per nucleon. It's an absolute total fluke that they both have the number 7 in them. Now what we're going to do is we're going to do the same thing for the fusion reaction. So we want to find out how much energy per kilogram there is using units of joules per kilogram. I have the numbers that we got from that part of this example on the right-hand side, and we got 2.826 multiplied by 10 to the negative 12 joules. We're going to divide that by the mass of the reactant. Okay, the reactant again is always on the left-hand side. So the reactant in this case has two pieces, hydrogen 3 and hydrogen 2, so I need to add those together in brackets when I divide by that. 5.0082 multiplied by 10 to the negative 27 plus the hydrogen 2, which is 3.3444 multiplied by 10 to the negative 27. I'll just double check my entries here. 2.826 times 10 to the negative 12 divided by those two masses added together look okay. What I get is approximately 3 times 10 to the 14 joules per kilogram. And as well, we can evaluate the energy content in this nuclear change by looking at electron volts per nucleon. We take the number of electron volts, which is 176,62500, and divide by the number of nucleons. Well, we only had 5 nucleons. There are 3 nucleons in the hydrogen 3 and 2 in the hydrogen 2. We get a whopping 3.5 times 10 to the 6 electron volts per nucleon. And just to keep track of things here, everybody, even though the total energy produced during the fission reaction, I'm going to highlight it for you, even though the total energy produced during the fission reaction of negative 2.79 times 10 to the negative 11 joules, or 174 million eV, even though that energy was more than the energy produced by the fusion reaction, when you measure the energy content in joules per kilogram or electron volts per nucleon, fusion wins out. You get approximately, I'm looking at the fusion now, 3.5 million eV per nucleon. Whereas in the fission reaction, you're getting about 0.7 million eV per nucleon. Fusion has a lot more energy content per unit of reactant, which is another reason why we would like to get fusion nuclear reactors up and running. There's so much more energy to be had so that we can live our lives in comfort. We have one more thing that we want to do though. We want to compare fusion and fission to the energy released when you have a chemical change. And this is bordering on a calorimetry question from Chemistry 30, except I'm giving you the energy here. It says that if you burn ethanol, you get approximately 1.4 times 10 to the 6 joules of energy if you burn 46 grams of the fuel. And you're asked to compare the energy released by chemical reactions, nuclear fusion, and nuclear fission. Well, the only useful comparison we have is the joules per kilogram. Fission worked out to approximately 7 times 10 to the 13 joules per kilogram. Fusion worked out to, I believe, 3 times 10 to the 14 joules per kilogram. So how many joules per kilogram would this chemical reaction produce? Well, we know the number of joules. It's 1.4 multiplied by 10 to the 6, and we know the mass is 0.046 kilograms. So this is a pretty trivial thing for us to be able to calculate. 1.4 multiplied by 10 to the 6 divided by 0.046 is 3 times 10 to the 7. A number of things are important when you start talking about the physics of producing energy. Chemical changes do not produce much energy at all. When you compare either fission or fusion to chemical, you're talking about 10 to the 6 to 10 to the 7 times more energy for a nuclear change than for a chemical change. When you compare fission and fusion, I'm thinking that fusion is about 4 times more energetic in joules per kilogram than fission. Let's just check this out. If I take 3 times 10 to the 14 and divide by 7 times 10 to the 13, I get a little more than 4. And what this means graphically, everybody, is that if you were to put these 3 processes on a graph, chemical energy doesn't even really register in the same arena as fission and fusion do. And fission is miles ahead, figuratively speaking, of chemical, but fusion is even further ahead in terms of energy availability per kilogram. All right, that is it for the lesson, and that is it for this modified version of Physics 30. I want to thank everybody for your patience as I work through some difficulties in getting things running initially, and I also want to thank you for your hard work. Don't forget that your final assessment is due this Friday at 3:15. The material that was presented to you Monday on radioactive half-life and the material presented in this lesson on fission and fusion are not covered in your final assessment. But as a physics teacher, I feel obligated to go through that material anyway because many of you will go on and take physics in post-secondary. Bottom line is these 2 assignments, the one you got on Monday and the one you're looking at now, are totally optional. If you do want some practice in calculating energies with fusion and fission, you can look at questions 1 to 4 on the next page. I hope that you have a wonderful rest of the day and a great rest of the week, and I hope to talk to you soon. Take care of yourselves, okay?